Hello everyone, a very good evening to all. Sorry for a few minutes of delays because there are some situations here in the lab. So, I am Vivekanand Nayak. I once again welcome you all for this fifth interaction session on Atomic and Molecular Physics course, which is being float by NPTEL this January 2026 session with course code NOC 26PH18. So today we will be solving a few problems covering the concepts of week 3 course contents. So if we discuss about the concept that was covered, so again fine structure of spectral line, the continuation discussion of fine structure of spectral line was conducted in the week's lecture. So week 5 course contents. So the fine structure of spectral line, that discussion was continued. Then new concepts related to multi-electron atoms was discussed. Multi-electron atoms were discussed. So if you talk about the concept of multi-electron atoms, then since there are more than one electron, so there will be effect of spin and orbital angular momentum. So that led to consideration of vector atom model. So vector atom model, basically it is a concept. It is used to explain how different angular momentum in an atom they combine. So again the vector atom model was also discussed to understand the fine structure and the spectral terms coming out of the interactions in multi-electron atoms. So vector atom model concept was also discussed. Vector atom model. Then due to if more than one electrons are present, then there will be spin orbit interaction, out of which the concept of LS and JJ coupling was covered. And then to arrange the electrons, because since electrons in multi-electron atoms, the electrons had to be arranged in increasing order of their energy. So ground state, the infrastructure like that. So for that arrangement, the concept of Abba's principle was also discussed. Abba's principle. So if you talk about LS coupling, LS and JJ coupling. So as you can clearly see here, it is capital N and capital S. So LS coupling, basically it is otherwise called as Russell-Saunders coupling. What happens basically in the LS coupling occurs mainly in light atoms. In light atoms, that is low Z values. Low Z values. So when the number of low Z values means the electrons are also less. So when there are lesser number of electrons, then the spin orbit interaction is weak. So in that case, the spin and orbit interaction is weak. But you must be getting confused with the name. Why it is LS coupling? Again, L is orbit and AS is spin. So spin orbit, it is again based on spin orbit interaction. But no, here it is talking about the spin orbit interaction of individual electrons. So here, due to lesser number of electrons, the spin orbit interaction of a particular electron that does not occur. So what happens for a large number of electrons, the orbital angular momenta they first combine, and then the spin angular momentum they gets combined with each other to produce L. So that's why this is capital L. So capital L is basically L1 vector plus L2 vector plus L3 vector, like that. So it is vector addition. So the individual orbital angular momentum of electrons they combine to produce capital L. Similarly, small is S1 vector plus S2 vector plus S3 vector plus, so they combine to produce capital S. Then LS coupling occurs. and it gives rise to J vector, which is L vector plus S vector, and then spectroscopic term arises, which is represented by the spectroscopic term notation 2s plus 1 Lj. So this is the concept of LS coupling. Now, if you talk about JJ coupling, then JJ coupling is small j, it will become small l plus small s. Then this is for individual electrons. Then this is L1 plus S1 J1. Then J2 is L2 plus S2, like that. So basically, it occurs in heavy atoms, that is large Z values. So in that case, then the total angular momentum J vector comes out to be J1 vector plus J2 vector plus J3 vector. But since there are more number of electrons in heavier atoms, so here the spin orbit interaction is strong, so it dominates. That leads to uh, the combination of orbital and spin angular momentum to produce total angular momentum J. So this is about LS coupling. We will solve a few problems that will basically covering those concepts. Again, another concept was Abbas principle. So Abbas principle basically says how the electrons are getting arranged in a multi-electron atom in increasing order of their energy, which are basically based on the n plus L values. So with this, let's start solving the sample problem that will be covering those concepts that I discussed now. So the question says, write all the possible spectroscopic terms corresponding to orbital quantum number L equals to 2 and spin quantum number S equals to 1. So it says, write all possible spectroscopic terms. So we need to find out all possible spectroscopic terms which corresponds to orbital quantum number L equal to 2 and spin quantum number S equals to 1. So we have L equal to and S equal to 1, and it is a single electron. So options are option A 2s half 2p3 by 2 3d3, option B 2s half 2p3 by 2 3d3 by 2, option C 3d1 3d2 3d3, or option D 3p half 3p3 by 2 and 3d3. As you can see here, these spectroscopic notations, they corresponds to LS coupling because these are represented by the notation 2s plus 1 Lj. So here we need to apply the concept of LS coupling. So I'll give you a few minutes to try this question and find the correct answer, and then we will discuss in more details how we will get the correct answer. So if we solve it, so here it says all possible spectral terms corresponding to the orbital quantum number L equal to 2 and spin quantum number S equal to 1. So basically L equal to 2 means, so since it's a single electron, we can write capital L equal to 2 and capital S equal to 1. Then we know J vector is L vector plus S vector. So it will be L vector plus S vector mod to L vector minus S vector mod. It is 2 plus 1 to 2 minus 1. So 2 plus 1 is 3, 2 minus 1 is 1. So it will be 3, 2 and 1. So the possible values of J coming out of this combination of L and S is 1, 2, 3. So J is 1, 2, 3 and L is 2, S is 1. So S is 1 means 2S plus 1 is 2 into 1 plus 1, which is 3. L2 means D, so it will be 2S plus 1 LJ, that implies 3D 1, 2, 3. So it is basically 3D1, 3D2, 3D3. So the correct answer is option C, 3D1, 3D2 and 3D3. So the possible spectroscopic terms corresponding to orbital quantum number L equal to 2 and spin quantum number S equal to 1 is 3D1, 3D2 and 3D3. With this we come to the next question. The question says write the possible values of L, S and J for PD configuration. So you need to keep this in mind. PD configuration under LS coupling, where S is 0, 1, L is 1, 2, 3, J is 0, 1, 2, 3, 4. Option B, S is 1, L is 1, 2, 3, J is 1, 2, 3, 4. Option C, S is 0, 1, L is 1, 2, J is 0, 1, 2, 3. Or option D, S is 1, L is 1, 2, J is 0, 1, 2, 3. So these are the four options, and here we need to find out only the possible values of L, S and J. We don't need to write the spectroscopic terms here. So the options are also given in terms of L, S and J values, not the spectroscopic terms. And here we need to find out for PD configuration. PD configuration. So that means one electron belongs to P subcell and the second electron belongs to D subcell. So for P there will be different value of L, for D there will be different value of L. So we need to apply those conditions here, and then we need to find out the possible values of S, L and J. So I'll give you a few minutes and then we will discuss. So if we solve it, so now we have one electron for p orbital, another electron for d orbital. So for p electron, L1 is 1 because S P D F, so L is 1, and S1 is half. For d electron, L2 is 2 and S2 is half. So now if you talk about LS coupling, then L will be L1 plus L2 to L1 minus L2 mod. So it is 1 plus 2 to 1 minus 2 mod. So it is 3, it is 1, sorry. So 3, 2 and 1. Similarly, S will be S1 plus S2 to S1 minus S2 mod. So it is half plus half, half minus half. So which is 0 and 1. So we have L equal to 3 to 1, S equal to 1 and 0. So now what are the possible J values? So when L is 3, S is 1, then J will be 3 plus 1 to 3 minus 1. So J will be 3 plus 1, 4. 3 minus 1 will be 2. So 2, 3, 4. L 3, S 0. So J will be 3 only because 3 minus 0, 3 plus 0, it is same. Similarly, L2, S1. So J will be 3, 2, 1. 3, 2, 1. Then L2, S0. J will be 0. Sorry, J will be 2. Then L1, S1. J will be 0, 1, 2. Then another is L1, S0. J will be 1. So what are the possible values of L, S and J we got? So the possible values of S is 0 and 1. So there are two options A and C, where S is 0 and 1 and L is 1, 2, 3 and J is 0, 1, 2, 3, 4. So the correct option is option A, where S is 0 and 1, L is 1, 2, 3 and J is 0, 1, 2, 3, 4. As you can see here, 0, 1, 2, 3, 4. So I hope this is clear to everyone. Now we'll move to question number 3. Question number 3 says, non-equivalent electrons are the electrons belonging to different subgroups. Consider the sp configuration of two such electrons and write all the possible values of S, L and J under LS coupling. So the options are option A, S equal to 1, L equal to 1, J equal to 0, 1, 2. Option B, S equal to 0, 1, L equal to 1, J equal to 0, 1, 2. Option C, S equal to 1, L equal to 0, 1, J equal to 0, 1, 2. Or option D, S equal to 0, 1, L equal to 0 1, J equal to 0 1. So these are the four options, and we need to find out the possible values of S, L, and J for non-equivalent electrons. So what are the non-equivalent electrons? So the non-equivalent electrons are those electrons, those basically corresponds to different subgroups. Different subgroups means uh, here you can see here it is sp. So for s the values of l s are different, for p the values of l and s both are different. So here we have different values of l and s. So basically they belong to different subgroups. So we now need to find out the possible values of l, s, and j for those two non-equivalent electrons. So these are the four options. I'll give you a few minutes and then we will discuss. So if we talk about non-equivalent electrons, then for s electron, L1 is 0, S1 is half. For p electron, L2 is 1, S2 is half. Now, if we talk about the coupling, then L vector will be L1 vector plus L2 vector. So it is 0 plus 1. So it is 1 only. And S will be S1 vector plus S2 vector. S1 vector minus S2 vector. So it is half plus half, 2 half minus half. So it is 0 and 1. So L is 0, S is 0 and 1. So J values when L 0, S 0, J is 0. When L 0, S 1, J is 1. So we have L values as 0, S values as 0, 1, and J values as 0 and 1. Sorry, L is 1, not 0. L is 1. So L1, S0, that means J is 1. L1, S1 means J is 1, 2, 3. So 0 is not possible. 1, 2, 3. So L is 0, S is 0, 1, and J is 1, 2, 3. So the correct option is S is L is 1, S is 0, 1, and J is 0, 1, 2. 1 plus 1 is 2, 1 minus 1 is 0, so it is 0, 1, 2. So S is 0, 1, L is 1, and J is 0, 1, 2. So the correct option is option B. Now we move to question number 4. So question number 4 says the orbital and spin quantum numbers of two electrons in a two valence electron atom are L1 equals to 3, S1 equals to half, and L2 equal to 1, S2 equals to half. But here we need to find out the possible combinations of J1 and J2 under JJ coupling. So it is a question related to JJ coupling where we have two valence electrons and L1 is 3, S1 is half, and L2 is 1, S2 is half. So these are two distinct sets of L1, L and S values for two electrons, and here we need to apply the concept of JJ coupling to find out the correct answer. So options are option A 1 by 2 3 by 2, 1 by 2 5 by 2, 1 by 2 7 by 2. Option B 1 by 2 3 by 2, 3 by 2 7 by 2, 3 by 2 7 by 2, 5 by 2 7 by 2. Option C 1 by 2 3 by 2, 3 by 2 5 by 2, 3 by 2 7 by 2, 1 by 2 7 by 2. And option D 1 by 2 5 by 2, 1 by 2 7 by 2, 3 by 2 5 by 2, and 3 by 2 7 by 2. So these are the four options. I'll give you a few minutes and then we will discuss in more details what will be the correct answer. So if we solve it, we have L1 3, S1 half. So J1 will be 3 plus half to 3 minus half. 3 plus half is 7 by 2. 3 minus half is 5 by 2. Then for 2, L2 is 1, S2 is half. So J2, small J2. So small J2 will be 1 plus half, 3 by 2, and 1 minus half, half. So what are the possible values of J1, J2? So J1, J2 we need to arrange. So J1 we got 5 by 2, 7 by 2. J2 we got 1 by 2 and 3 by 2. What are the possible values? 5 by 2, 1 by 2, 5 by 2, 3 by 2, 7 by 2, 1 by 2, 7 by 2, 3 by 2. So these are the four values: 5 by 2, 1 by 2, 5 by 2, 3 by 2, 7 by 2, 1 by 2, 7 by 2, 3 by 2. So what will be the correct option? So 1 by 2, 5 by 2, 1 by 2, 7 by 2, 3 by 2, 5 by 2, 3 by 2, 7 by 2. So the correct option will be option D. Now we move to question number 5. Question number 5 says, if atoms could contain electrons with principal quantum numbers n up to n equal to 6, how many elements would be there? Consider that there is no restriction of maximum number of electrons in an orbit. So this is a very important question. So options are option A 92, option B 102, sorry, option B 110, option C 182, or option D 196. So the question says, if atoms could contain electrons with principal quantum number n equals to 6, that is the maximum value of n, it can only be 6, then how many elements will be there? So what will be the maximum number of electrons? So consider that there is no restriction of maximum number of electrons in an orbit. So we are not talking about the orbits. So here we need to find out up to n equal to 6, what if the maximum value of principal quantum number would have been 6, then what will be the maximum number of electrons in an orbit? Sorry, what will be the maximum number of elements that can be possible up to n equal to 6 principal quantum number? So I'll give you a few minutes to think about this question, because it is a good question, and you need to think a bit to answer it correctly, and then we will discuss what will be the correct answer. we know for a particular value of n, the maximum number of electrons it can contain is 2n square. So for n, maximum number of electrons is 2n square. So for n equals to 1, 2n square is 2, n equal to 2, 2n square is 8, n equal to 3, 2n square is 18, n equal to 4, 2n square is 32, n equal to 5, 2n square is 50, n equal to 6, 2n square is 72. Now if you add all these values, it will be 182. So how 2n square is coming into picture? Because we know the maximum number of electrons that can be contained is 2l plus 1 in L subcell, and the value of L, it varies from L equal to n minus 1, sorry, L equal to 0 up to n minus 1. So we are getting 2n square, the maximum number of electrons for a particular value of n. So 182 will be the correct answer, option C, 182. Now we move to question number 6. Question number 6 says, calculate the angle between the total angular momentum vector J and orbital angular momentum vector L for 3p1 state. Options are option A 30 degrees Celsius, or sorry, 30 degrees, option B 45 degree, option C 60 degree, and option D 90 degree. So we have already solved this type of problem in past interaction sessions. So the angle between L vector, so here you need to find out the angle between J vector and L vector. It is but initially, previously we had already discussed about L vector and S vector. So we had used a formula where J vector is L vector plus S vector mod. Then we had a dot product J vector, J vector is equal to L vector plus S vector dot L vector plus S vector. Like that we had calculated, but here is J and L. So in that case the formula will be different. So here what will be the formula? We know J vector is L vector plus S vector. Since we need to find out the angle between J and L, so we need to make J vector minus L vector. So in that case, S vector dot S vector will be J vector minus L vector dot J vector minus L vector. So in that case, it will be J square plus L square minus 2 L vector dot J vector. So in that case, what will be cos theta? Cos theta will be J square plus L square minus S square divided by 2 J vector mod into L vector mod. So we know J square is given by J into J plus 1 H cross square plus L into L plus 1 H cross square minus S into S plus 1 H cross square divided by 2 J into J plus 1 root over into L into L plus 1 root over H cross square. So H cross square gets cancelled out. So it is J into J plus 1 plus L into L plus 1 minus S into S plus 1 divided by 2 J into J plus 1 root over into L into L plus 1 root over. So and it is for which level? 3p1 state. So for 3p1, 2s plus 1 is 3, so s is 1, P means L is 1, SP, and J is 1. So what will be cos theta? So cos theta will be J into J plus 1, 1 into 1 plus 1 plus L into L plus 1, 1 into 1 plus 1 minus S 1 into 1 plus 1 divided by 2 into 1 into 2 root over 1 into 2 root over. So it is 2 plus 2 minus 2 divided by 2 into 2. So it is 2 by 4, that is half. So theta is cos inverse half, which is 60 degrees. So the correct answer is option C, 60 degrees. I hope this is clear to everyone. Now we move to question number 7. So question number 7 says write the electronic configuration for chromium. So these are the options. Option A 1s to 2s to 2p6 3s to 3p6 4s 135. Option B 1s to 2s to 2p6 3s to 3p6 4s to 3d4. Option C 1s to 2s to 2p6 3s to 3p6 3d5. Option D 1s to 2s to 2p6 3s to 3d5 3p5 3d7. So this we need to arrange according to the Abba's principle in increasing order of their energy considering the n plus l values. So I'll give a few minutes and then we will discuss. If you talk about the electronic configuration for chromium, so according to Abbas principle, in increasing order of their energy, what is the way to write? It is 1s to 2s to 2p6. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So for chromium it is 24, Z is 24. So 1s to 2s to 2p6 10, 3s to 3p6, 4s to. So for chromium 24, it should be 1s to 2s to 2p6, 3s to 3p6, 4s to 3d4. So it should be like that. But it is not the case, because we know half filled or fully filled subcells, they are more stable, because due to energy exchange, symmetry, and reduced repulsion, when the electrons are arranged in an orbital which is completely filled or completely half filled, in that case they are more stable. So it will become 1s2, 2s2, 2p6, 3s2, 3p6. It will be 4s1 and 3d5. So what happens here? If you see, in case of 4s2, 3d4, and 4s1, 3d5. So 4s2 means it is fully filled, and 3d4 is 1, 2, 3, 4. So it is not half filled. But here this is fully filled and this is not half filled. But here in 4s1 it is half filled, and in 3d5 it is also half filled. So it is half filled and it is again half filled. So they have identical spin, because here it is half, here for electron it is half, half. So here the due to exchange in energy, it will be more stable. So in that case, the correct configuration is 4s1 3d5, which is the correct answer. So 4s1 35, option A is the correct answer. Now we move to question number 8. So question number 8 says, consider two electrons, one in 4p subcell, another in 4f subcell. Obtain the possible values of L and S. So over here, as you can see, N is same. For P, what are the for P, what are the values of L? So L1 is 1, S1 is half. For F subcell, L1 is 3, S1 is half. So what will be so L1 is 1, L2 is 3, S1 is half, S2 is half. So in that case, what will be L? L will be L1 plus L2 to L1 minus L2 mod. So it is 1 plus 3 to 1 minus 3. So it is 4. It is 2. So 3. So 2, 3, 4. These are the possible values of L. And similarly S, it is half plus half to half minus half. So it is 1 and 0. So what are the values of L and S? So L is 2, 3, 4, and S is 0 and 1. So the correct option is AC 0, 1, L is 2, 3, 4. That is option B is the correct option. Now we move to question number 9. So question number 9 says, write the values of quantum numbers uh, uh, S, L, and J for the spectroscopic term 2s half. Options are option A. So it is 2s half. So 2s half means 2s plus 1 Lj. So 2s plus 1 is 2. That means S is half. Then L is S. So L is 0. Then J is half. So J is half. So S is half, L is 0, J is half. So S is half, L is 0, J is half. So option A is the correct option. Now we move to question number 10. Question number 10 says, the electronic configuration of carbon atom is 1s to 2s to 2p2. It has two equivalent electrons in outermost piece of shell. Write all the possible states for this. Options are option A 1s0, 3s1, 1p1, 3p0, 3p1, 3p2, 1d2, 3d1. Then option B, C, D, all options are given. So we need to find out what will be the possible states when it has two equivalent electrons, two equivalent electrons in outermost p cell, which is 2p. So we need to find out the possible states for this. So I'll give you a few minutes and then we will discuss. So now I think the options given here is not correct. So here I see it has two equivalent electrons. So for two equivalent electrons, so let for p electrons, L1 is 1, S1 is half, L2 is 1, S2 is half. So that will be L will be 0, 1, 2, and S will be 0 and 1. So what will be the J values? So L0, S0, J will be 0, L0, S1, J will be 1, L1, S0, J will be 0, sorry, J will be 1, L1, S1, J will be 0, 1, 2, L2, S0, J will be 2, L2, S1, J will be 1, 2, 3. So here, if you see, uh, for P, since both the electrons are present in P, that is 2P, since they are equal electrons, so no two electrons can have all four quantum numbers equal. So in that case, if you apply this rule, only the possible combinations of L and S which is even, they are only possible. So here L plus S is 0, so it is possible. Here L plus S is even, so or it is not possible. So again it is not possible. Here 1 plus 1 2, it is possible. Here 2 plus 0 2, it is possible. 2 plus 1 3, it is not possible. So the possible values of j is coming out of L equal to 0, S equal to 0, then L equal to 1, S equal to 1, and L equal to 2, S equal to 0. So if you write the values, so the allowed terms are 3p, 1d, and 1s. So 3p is this corresponds to 3p, this is 1d, and this is 1s. So it will be 3p 0 1 2, then 1d 2, and 1s 0. So the correct answer will be 3p 0 1 2, 1d 2, and 1s 0. So with this we come to the end of today's interaction session. I hope the questions that I have solved today will definitely help you in solving your course assignments as well as if you are preparing for your exam. With this, I end today's interaction session. In the next interaction session, we will be solving a few problems based on week 6 lectures, and we will deeply discuss about the concepts covered in that week lecture. Thank you all. Have a great day.